Hello. We have talked about how we are typically going to be using the op-amp when we are using it in most linear amplification and other mathematical solving operations. We're going to be using it in a negative feedback configuration. And so we're going to be studying the effect that connecting the amplifier in negative feedback has over the amplifier parameters. Specifically, what effect does negative feedback configuration have over the gain of the amplifier, as well as the input-output characteristics, input resistance, output resistance. And so we're going to start with a general coverage or review of a general feedback amplifier. And I have drawn a block diagram of this amplifier. Normally, the amplifier in open loop will just be the block labeled as amplifier A, with a particular gain. Let's imagine a voltage amplifier. In this case, we'll have a voltage gain, for example. And then there is a source that provides an input signal to the amplifier, and there is a load, which is basically where the amplifier sends the output signal. When we add a feedback network, the feedback network, what it does is it samples the output and it feeds it back to the input of the amplifier. And there are two possible ways of feeding it back. The sampled output can add to the input signal, in which case you will have positive feedback, or it can be subtracted from the input signal, in which case you have negative feedback. So for example, if our source provides an input signal, let's call it x sub I, I'm going to label them in a different color, x sub I. That input signal is fed through the amplifier. The amplifier is going to provide an output signal, x sub O. And then that signal is going to be sampled, sent through the feedback network with a feedback factor beta. And so basically the feedback signal that you get out of it is going to be feedback signal beta times x out. And this signal in a negative feedback amplifier will be subtracted from the input signal, and we represent that by adding a minus sign next to the summing symbol. And so the input signal gets added, but the feedback signal gets subtracted. And so what you end up with is an error signal at the input of the amplifier. And the error signal x sub b is going to be equal to the input signal from the source xi minus the feedback signal xf. And then the output of the amplifier obviously is going to become the gain times whatever signal was fed into the input of the amplifier, which is the error signal. Okay. So to put that mathematically, again, if the error signal is equal to the input signal minus the feedback signal, then I can express my output signal, x out, as A times my error signal, which again can be expressed as A times the input signal xi minus the feedback signal x sub f. And we just said x sub f is beta times the output signal, so I can again express this as A times xi minus beta times x out. And so I can manipulate this expression, put all the x out terms on one side of the equation, all the x in terms on the other side of the equation, and end up with an expression that x out is equal to, or x out plus beta x out, so x out 1 plus beta, A times beta rather, is equal to A times xi. And therefore, if I want to come up with an expression for the closed loop gain of the amplifier, it's no longer the gain of just the open loop amplifier, but rather the gain of the overall negative feedback system. That's going to be the ratio of x out to x in, which is going to be A divided by 1 plus A times beta. And this is an important result. It's the expression for the closed loop gain of a negative feedback amplifier. And it tells us that it is equal to the open loop gain divided by a factor. So essentially what we're seeing is a reduction in the open loop gain of the amplifier once we connected in negative feedback. And the reduction is by a factor 1 plus A times beta. And because this parameter appears, or this quantity appears often in the analysis of feedback circuits and feedback systems, A times beta, it receives a special name. It's termed the loop gain. And so a little bit of terminology here. Beta is typically referred to as the feedback factor. A times beta is referred to as the loop gain because it is the overall gain as you go through the loop is the product of the gain of the amplifier times the feedback network. And 1 plus A times beta is termed the amount of feedback. Okay. So we can see already the first effect to note, and that is that adding negative feedback decreases the gain. And again, that's an important result, but we can take a closer look at this expression. And if we, let's say, divided the numerator and the denominator by a factor of A times beta, a factor of the loop gain, so divide numerator and denominator by A times beta, and we are left with the following expression for ACL. ACL is equal to 1 divided by beta, after I divide the numerator by A times beta, and all that divided by 1 plus 1 over A times beta. And now we can see that if A times beta, if the loop gain is a large number, much larger than 1, then the denominator is going to be approximately equal to 1, which means that the overall closed loop gain will be approximately equal to 1 over beta. And that is also an important result. So note that if A beta is much larger than 1, then 1 plus 1 over A beta is approximately equal to 1. And therefore, the closed loop gain is approximately equal to 1 over beta. And again, why is that an important result? And the answer is because notice that the new expression, or this approximation for the closed loop gain, is now independent of the open loop gain. It's only dependent of beta, which is the feedback network. And the feedback network is typically going to be comprised of resistors and other components, capacitors, etc., components that we are able to get precise values for, whereas the open loop gain, let's say, of an op-amp is a parameter that we typically don't have a lot of control over, and it varies over a wide range. Even for the same op-amp, if we were to look at the datasheet, if they were to give us like a maximum and minimum value, which more often than not, they'll just give you a typical value. But we will see that there is a lot of variation or a wide range. And the reason for that is because it's a parameter that gets heavily affected by process variations. And so using negative feedback, we can now design amplifiers that have a stable gain by using as the starting point maybe an op-amp whose open loop gain is not a very stable parameter. So we have decreased our gain, but we have gained in gain stability. So we have desensitized the gain from process parameters, process variations. And that's an important result. And so note that for large values of open loop gain, ACL, the closed loop gain, becomes independent or almost independent of the open loop gain. And depends only on feedback network. And therefore, we have achieved negative feedback increases gain stability. And next, we're going to take a look at how the different types of negative feedback affect the input resistance and the output resistance of amplifiers. Thank you.